We established last time that we all have perfect timbre. Now, in order to do a lineup of instruments and actually be able to identify all of them by ear, you would need familiarity with those instruments. But I guarantee you that any instruments you've been around regularly in your life, whether they're at your house or if you play in a band or orchestra or rock band, any instrument you really know, I would guarantee you'd be able to identify it by ear. Today isn't about learning to identify all of the instruments by ear. It's about studying the differences that we can see in the spectrogram and hear with our ears between those instruments. So, as a litmus test, we're going to take each instrument that I've picked here, 15 different instruments, and listen to them back to back, playing the same note. That way we get rid of the difference of pitch, and they're all long notes, so we're not really thinking about the difference of rhythm. We're just focused on the difference of timbre. Oh, I forgot to say. Grab your sparkling hop honey water, and let's go. So in order, they're flute, clarinet, oboe, bassoon, French horn, trumpet, tuba, violin, cello, guitar, it's a classical guitar, piano, marimba, vibraphone, tai gong, and a synthesizer playing a square wave. Flute, clarinet, oboe, bassoon, French horn, trumpet, tuba, violin, cello, guitar, piano, marimba, vibraphone, tai gong, and synthesizer with a square wave. So, we can see differences both in their waveforms and also in their spectra. So you notice some of them look rather similar and others look very different. Let's talk about what they look and sound like. Timbre, as we discussed last time, is something that we're very good at identifying the differences, but it can be hard to explain the differences, just like it's hard to explain what timbre is. It's this. It's all these different timbres of different instruments on the same note. So notice how, for example, here we see the guitar. We can describe its timbre both through the waveform and frequency spectrum. We can see that the guitar has a lot of frequencies, a lot of partials at the very beginning. Notice right here, we see a lot of vertical, so a lot of frequency partials. And we see a lot of them continue, but they die off as the bottom or the fundamental frequency continues on. The same is true with the piano right here. Insofar as a lot of the higher frequencies die off, but they're there at the beginning. So we notice that with these string instruments, we have a lot of harmonics or a lot of partials at the beginning. They die away, but the lower partials or harmonics continue on as the string continues to resonate. That's because the way that we activate those strings in the case of the guitar is by plucking, and in the case of the piano is by hitting them with a hammer, the little hammer inside the piano. So when they're first hit, we hear all this complex information from the string. We hear all the higher harmonics, but as it continues to ring, it's no longer being plucked. So we just hear the lower parts. The first two instruments, I'm going to zoom in on those. The first two were the flute here and the clarinet. Let's hear those again and look at the spectra. Some differences we can see are the clarinet here has louder partials on the odd numbers 1, 3, 5, whereas the flute seems to be pretty equal in volume. Remember, the volume is the color, so these more red or darker lines are quieter than these yellow ones, which are very loud. And this program lets me isolate each harmonic, so we can just hear, if we want to, this. And we can hear how its second harmonic is quieter. Let's hear that again. Whereas with the flute, both are loud. So there's these differences in volumes between the harmonics, and that's one of the main things that contributes to the timbral difference. You notice this noisy static in between here. That's the breath of the flute. So when we hear the flute sound, we know partly that it's a flute because we hear so much more breath coming through. So let's listen to that. I can't isolate each of these little segments in between the harmonics, but here's just one of them. It's a little bit like hissing. So you notice when the cleaner sounds like this has less breath in it because we see less staticky mush in between. So that was the oboe, and there's a lot less air that escapes when playing into the whoops. This is the tuba, and this is the trumpet. So we hear a difference of timbre for sure. We notice that the tuba does have more breath escaping. This is also a lot higher in the range of the tuba, so it's harder to play. It's up high on the tuba. It's right in the middle of the range of the trumpet. Notice looking at the very end to the synthesizer that there's a clear missing harmonic scheme that's going on. All of them have the fundamental, the bottom harmonic. As we go up the harmonic series like this, you can see all the ones that do and don't have the second harmonic, the third harmonic, the fourth harmonic, and the fifth harmonic. You notice a pattern over here with the square wave. The square wave synthesizer has a pattern of harmonics 1, 3, 5, 7, etc., all the odd harmonics. It's often compared to a clarinet because, looking back again at the clarinet, it has louder harmonics on 1, 3, 5, 7 than it does on the odds. It still has the evens. The odd ones are louder. The evens are still there, but they're quieter. So the differences of timbres could be described acoustically as being a difference in the volume of the harmonics, a difference in the way that they sound at first versus as they sustain, or what's known as the attack transients versus the sustain, the amount of air or noise that's in between the harmonics, the way that the harmonics subtly move or vary. Some of these you see a little bit of vibrato, others are more pure and straight. Taking the example of the vibraphone, this piece of metal is just very, very pure and straight here. Whereas you can see in this piano, there's a little bit of variation to the volume of some of these harmonics. You can see this one dipping in and out, and that's just part of what creates the sense of timbre. And just notice again, finally, that the synthesized sound is very perfect, pure, and unchanging. and that's part of what gives it its characteristic sound. Tai gong. Let's hear it again. We do hear the pitch of the Tai gong. You can see that it has the first harmonic. It also has the second harmonic. Then it's missing a lot in this range. But then up here it has what appears to be the sixth harmonic, but then some other partials in between. So even when the pitch stays exactly the same, instruments can differ in several ways. Which partials are present, how loud those partials are, how the spectrum changes over time, how much noise is mixed into the sound or breath, how stable or irregular those frequencies are, and all of those differences contribute to what we hear as timbre. And that's how we know what instruments they are. So next time we'll be talking about a history of instruments and how they came to develop and look and sound the way they did in the first place. I'll see you there.